Hi everyone, I am Jack Kang. I'm going to present our final project on behalf of Group 3. Our project title is Predictive Models for Compliance with COVID-19 Restrictive Measures. Here is the outline of my presentation. I will first introduce some background information related to this project, and then I will briefly go over the public data set we use to build predictive model, and then I will show our results in different sections. The coronavirus disease 2019 or COVID-19 pandemic has been affecting people worldwide since its first detection in China in the end of 2019. It's a serious respiratory disease caused by SARS-CoV-2 virus. According to statistics from the World Health Organization, until early May, there has been a total of about 150 million cases globally. This figure shows the total number of cases in each country by May 4th, with darker color indicating more cases. As we can see, the COVID situation is most serious in Europe, South America, and the US. And if you follow the news, recently the situation is rapidly deteriorating in India. COVID-19 is a highly transmissible disease, and its transmission may occur before or without symptom appearance. Even with vaccines, measures such as quarantine and social distancing are still needed in terms of suppressing the spread of the disease. Therefore, countries around the world implemented various social control measures with different level of stringency, as shown in the plot below. In countries in face of serious infections, for example, in Europe and in South America, the daily activities are highly regulated by the government. The US is probably an exception since it has the highest number of cases, but also a relatively liberal regulation. Apart from pandemic regulation itself, general public compliance with the regulations or recommendations from health or governmental authorities is key to effectively control the virus spread. Therefore, understanding as well as predicting the overall compliance with these prevention measures are needed to inform policy decision making. Previous research has shown that demographic, psychological, and behavioral responses may shape the willingness to comply with public health measures. The figure below shows a theoretical model of health behavior. It contains four related variables: perceptions, feelings, attitudes, and intentions, as well as one dependent variable, the health behavior. This model reflects the hypothesis that perceptions about COVID-19 severity and susceptibility, feelings related to it, attitudes about the disease, and the intention to comply with advised preventive measures may influence the health behavior directly or indirectly. Demographic variables such as age and education level may also influence our perception about the disease or directly our health behaviors. To further contribute to the prediction of overall compliance with guidelines and restrictions during the COVID-19 pandemic, we used a large-scale dataset to examine psychological and demographic predictors of compliance with COVID-19 restriction measures. And these prediction models may provide insights to policymakers in terms of evaluating potential interventions before actual implementation. Next, I will go over the public data set we use for model fitting. We use the data from COVID eye stress survey that ran from March 30 to May 30 in 2020 by collaborators from 39 countries and regions. In total, about 170,000 participants were recruited from 179 countries on 6 continents. About 110,000 people with complete outcome information are included for model fitting. The outcome of interest in this study is compliance with COVID-19 restrictive measures. It is measured by 6 items, each of which has a score. So we categorize into 2 groups, compliant versus non-compliant, based on sum of scores across the 6 items. An individual is compliant if the sum of score is over the median and non-compliant otherwise. So in this way, we have 52.6% compliant people versus 47.4 non-compliant people in this data set. We selected 25 variables with low missiness, defined as missiness below 5%. as predictors for compliance. There are 11 demographic variables, for example, age, gender, and education level, and 14 psychosocial variables, including 5 personality traits, like openness to experience, conscientiousness, extroversion, agreeableness, and neuroticism, and 9 other variables measuring perceived stress, loneliness, and interpersonal and institutional trust. Specifically, each psychosocial measure corresponds to a multi-item question and is summarized to an average value, which is then used for model fitting. We also imputed missing values using mean for continuous variables and the most frequent group for categorical variables. Now I will show our result. Firstly, we did some exploratory analysis to see if compliance is differentially distributed across individual variables. Here I show a few of the examples. Note that all distribution I will show are based on data before imputation. In terms of demographic variables, we found that age is slightly higher in compliant group compared to non-compliant group. This varying plot on the left shows the distribution of age for the two compliance levels, and we can see that the difference in age is minimal for the two compliance levels, although it is significantly higher in compliant group, probably due to large sample size we have. We also check the proportion of compliance in different age groups as shown on the right. Age is cut into groups based on quantile at each quarter, and we notice that uh, there are slightly more compliant people as shown in light blue in older age group. We also check whether education level is associated with compliance in a univariate analysis. This plot shows the proportion of compliant and non-compliant people across different education levels, from no education at all to PhD degree. We did observe that higher education level appears to be associated with higher compliance. Furthermore, here, these two examples show distribution of certain psychosocial variables across the compliance levels. Specifically, we observe that average trust in institutions, for example, in health institution, in government, in a country's health system, and the average concern over COVID-19 are slightly higher in compliant people. Again, though the difference is significant, it is minimal in terms of absolute scale. Therefore, our exploratory analysis shows that there are a few variables that are slightly different across the two compliance level, which indicates that they could be weakly informative of the compliance. To rigorously check the predictive performance based on these predictors, we fit various classification models, and I will present their performance. We split the data into 90% training and 10% test data. And using the 25 variables I mentioned above, we fit in multiple classification models, including ordinary logistic model, panelized logistic regression, including Ridge, Lasso, and elastic net, as well as KNN and random forest. Tenfold cross-validation was used to determine the best tuning parameter for each of these models. Then we check the test error based on the test set and choose the best model based on overall accuracy. Now let's dive into model performance. This plot compares the cross-validation performance of the models we fitted under their best tuning parameters. Note that this is the performance calculated from the tenfold cross-validation within the training set. So it shows the mean accuracy and kappa across the tenfold and the corresponding 95% confidence interval. So based on accuracy, we see that random forest is the best model, while the lasso is the worst. However, looking at accuracy alone could be misleading. Imagine that we have an extremely imbalanced outcome, say 90% of class 0 versus 10% class 1. Then a model that always predicts the majority class will have an accuracy of 90%, but it's actually very bad. So kappa is actually a more robust measurement compared to accuracy, since it takes account into the correct classification due to random chance in face of imbalanced outcome. So it is calculated using the following formula, but in brief, it compares the model to the one that always predicts the majority class, which has a kappa of 0. So the higher the kappa, the better the model. Therefore, based on kappa, random forest is still the best model. Nevertheless, kappa around zero point 0.2 really indicate that all of these models do not have good predictive performance. So cross-validation within the training set give us an estimate of the test error. So what would the test error uh, what would the test error actually look like when applying these models to a test set? So we did apply our fitted model to the health test set, and this plot shows the performance in terms of test error rate, kappa, false positive rate, and false negative rate for all the models. Based on these results, random forest in blue is the best model since it has the lowest test error rate, the highest kappa, and relatively low false positive and false negative rate. And surprisingly, ordinary logistic regression is the second best model since it has the shown in light blue here. It has the second lowest test error and second highest kappa, and also relatively low false positive rate and false negative rate. Lasso turns shown in green turns out to be the worst, since it always predicts compliant, as shown by a false positive rate of 1, a false negative rate of 0, and a kappa of 0. This indicates that a fancy and a more complicated method does not really guarantee better predictive performance. However, with about 35% test error rate and 45% false positive rate, I would say that none of these models really have ideal predictive performance. And lastly, we checked which variables are important in predicting compliance. These two plots shows the variable importance in the top two models, namely random forest and logistic regression model. And what is obvious is that the average concern over COVID-19, as shown encoded as COVID concern (AVG), is the most important predictor in both models. And if we look them more carefully, we also find that personality traits encoded as person dot something are also among the top predictors in the two models. They are ranked high in the random forest model and also relatively high in logistic model here. They are here, 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 and here, so pretty high. And measurements of trust are also relatively important. For example, trust in institution, trust in government, trust in people, and trust in country are ranked high in random forest model. And similarly, trust in country and trust in people are also among the top predictors for the logistic regression model. So in summary, we fitted ordinary and penalized logistic regression, as well as K and random forest models to predict compliance to COVID-19 restrictive measurements using various demographic and psychosocial variables. We found that random forest is the best model, but in general, all model performance are not ideal. And concern over COVID-19 is the most important predictor of compliance, and other relatively important predictors include personality traits, and measures of trust. And finally, our results also have the following limitations. Firstly, in our data set, the low-risk people are underrepresented. Actually, we have 68% of people being high risk, which is not really the real world case. This raises concerns about generalizability of the results. And secondly, we perform sort of naive imputation by plugging sample mean or the most common group, which may bias the data. And lastly, our data is cross-sectional, so we need to take extra caution when trying to interpret any association or finding. So this is the end of our presentation, and we welcome any questions related to our project. Thank you.